So do you remember what we did last time? We were talking about energy quantization in light and matter. And so today we're going to talk about thermal equilibrium also in light and in matter, which will lead us directly to lasers. Are we ready to do this? So when we say thermal equilibrium, what do we mean? When we say thermal equilibrium, what we mean is when a system is in thermal equilibrium, that implies there is no net energy transfer between the system and its surrounding. What is a system? A system is anything that is under consideration. And a surrounding is everything beyond that system. Very simple definition. If you are looking at a box, that's your system. If you're looking at this room, that's your system. If you're looking at this campus, that's your system. If you're looking at planet Earth with respect to the others, that's your system. Does that make sense? So it doesn't mean that the system itself has to be small or large. If you're looking at one atom, then that's your system. Anything under consideration is a system, everything around it is the surrounding. So for example, if my system is this table, what's its surrounding? But the room, starting with the room and beyond. But if I'm looking at this room, what's its surrounding? Fisher, like the building, and then the campus, and then everything around it. Does that make sense? So that's how you define a system. But when we talk about a system being in thermal equilibrium, we basically mean delta T equals 0. It doesn't mean that the system is at temperature 0. Yeah. It just means that it's not exchanging any temperature with its surrounding. Okay, good. So when I say that, how does this help me define for light and also for atoms? So I'm going to give you this little blurb before we start. All atoms are made of neutrons, protons, and electrons. Protons and electrons are charged particles. And all atoms emit and absorb light energy. So these are the three things I have told, well, two things I've told you. One is that all atoms are made of neutrons, protons, and electrons. And two, all atoms emit and absorb light. So now I'm going to talk about two different things. So when I say thermal equilibrium, I am going to do two different things. One, I'm going to discuss thermal equilibrium for electromagnetic waves. And two, I am going to talk about atoms in thermal equilibrium. When I say electromagnetic waves in thermal equilibrium, this will take me directly to black body radiation. And when I say atoms in thermal equilibrium, that will take me directly to what is called the Boltzmann distribution. So people from thermal, you heard the word Boltzmann distribution. For everybody else, that's okay. We will discuss it today. So don't worry about it. And for those who are planning to take thermal, raise your hands. Excellent. When we get to that point, I will remind you that you have seen this before. So they are used in multiple places. And that's so fascinating about physics is we cannot compartmentalize. They're the same things that are being used in multiple contexts. And that's fascinating. Just thinking about it.